Okay, so a quick video about rate graphs. What is a rate graph? Well, a rate graph is a graph in which we follow the result of a reaction. In this case, if we have a quick look, it is the volume of gas released against time. Now, it could be mass lost against time, it could be amount of precipitate produced against time, but it is the result of a reaction against time. We have to do this because we can't look at number of successful collisions directly because we can't see it, we can't measure it, we can't observe it. Okay, so given that, these sorts of graphs, what can we read off these sorts of graphs? Well, the rate of a graph of a reaction in a graph like this is given by the gradient, i.e. the steepness of the line, okay? And as might be obvious, the steeper the line, the higher the rate of reaction. So if we look at the rate graph below, a couple of things. One, you'll see that I've taken out the units because this is completely imaginary data, so I don't want real units down the side, but you should have real numbers down the side of your graph. I should have said I have left in units just as a sort of an advisory. This is, the volume could be in cm cubed, the time could be in minutes. So we do have some units there. What is this graph showing us? Well, at the beginning, the gradient is at its maximum. What's this telling us? This is telling us the rate of reaction is at its highest at the beginning of the reaction. Why is this? Well, at the beginning of the reaction, we have the maximum number of reactant particles. If we have the maximum number of reactant particles, we have the maximum number of collisions per unit time, maximum number of successful collisions per unit time, therefore the highest rate. It's not 100% clear from this graph that I've got on the diagram below, but during the reaction, the rate is always decreasing. Always decreasing, i.e. the gradient of the graph will decrease. Some people would look at it and go, but the line's getting higher. Yeah, the line might be going higher, but the gradient is always getting lower. It is a curve that is curving over, okay? What does this mean and why is this the case? Well, if the gradient is always decreasing, the rate is always decreasing. Why would the rate be decreasing? The rate would be decreasing because as the reaction progresses, we are using up reactant particles. If we have less reactant particles, we'll have less collisions per unit time, less successful collisions per unit time, and therefore the rate will go down. To the point where, and we can probably mark it with some accuracy on this graph, it's probably about here, that the line completely flattens out. If the line is completely flat, that means the gradient is zero. That means the rate of reaction is zero. That means the reaction has stopped. It has stopped at that point. Why will it have stopped? Because we will have used up all the reactant particles. If we have no reactant particles, we can have no collisions per unit time between them. If we have no collisions per unit time, we won't have any successful collisions per unit time. Therefore, we will have no reaction and the rate will be zero. So that's looking at a particular line and describing why one particular line looks like it does. At GCSE, you will be asked to do that, probably. You may also be asked to sketch extra lines onto the graph. So, in this pretend scenario, we are doing a reaction between magnesium and hydrochloric acid, which would give a salt magnesium chloride, because it's a neutralization reaction. Metal plus acid gives salt plus hydrogen. And as I just said, it gives off hydrogen. Now the hydrogen being given off, that's helpful because that is a gas. I can collect a gas either by connecting a gas syringe to a conical flask or connecting a delivery tube to a conical flask and then collecting the gas into an upturned measuring cylinder by downward displacement of water, which means that every so often, a set time interval, I can measure how much gas has been released, and that data would give me a graph, a plot, much like the one you see before you. So the plot before you is the black line. The black line, let's just highlight over, is this line here, which is given with this set of conditions. Now, I have decided not to mess around with temperature, so as is said at the bottom, all of the reactions are at room temperature. But just to quickly run through temperature, if I increase the temperature, I would give the reactant particles more kinetic energy, therefore they would move faster, which means, i.e. with more velocity, which means that they would have a greater number of collisions per unit time, greater number of successful collisions per unit time, and a greater initial rate, which means that my initial line would be steeper. But I haven't messed around with temperature, I've been messing around with other factors. So let's have a look at the blue line, which I'm going to sketch on in a minute. So let's compare the blue to the black. Okay, so black line, 2 grams of powdered magnesium. Blue line, 2 grams of powdered magnesium. We've kept that exactly the same. So we're using the same amount of reagent. And the powdered bit, why is the powdered bit important? Powdered is giving you the surface area, which is one of our variables. Black line, with an excess of 1 mole per dm cubed HCl. Mole per dm cubed being a measure of concentration. So mole per dm cubed, this is concentration. Let's just write that in so you've got that in there, concentration. Whereas the blue line is 0.5 mole per dm cubed of HCl. Now notice with both we're using an excess of HCl, so that means all the magnesium is being used up and we've got the same amount of magnesium. So that's not going to change. So this blue line, we're using up the same amount of stuff, 2 grams of magnesium, because that's the thing that's not in excess. But the concentration of the acid we're using is half. So what does that mean? Well, that means our initial rate is going to be lower, because if you decrease the concentration, you have less reactant particles per unit volume, meaning less collisions per unit time, meaning less successful collisions per unit time. So I know my graph needs to start off shallower because I'm going to have a decreased rate. Where does my graph finish? Not where does the reaction stop, but where does the graph finish? Well, I'm using the same amount of stuff, so I'm going to produce the same amount of gas. So I've got to start shallower, but finish at the same height. Not finish in the same spot, finish at the same height. So, starting shallower. Not easy to do on an iPad, but I'm starting shallower. To be honest, that line is not great because if I carry that line up, I'm going to finish up here somewhere. Trouble is, if I finish up there somewhere, I'm not proving to the examiner that I know I have produced the same amount of gas. So let's try that one again. Let's reverse that bit, let's reverse that bit. So I'm going to have to try again. I've got to start shallower and let's curve it in. There we go. Not too bad at all. Okay, let's just run through that again. It starts off shallower down here because I am using a less concentrated acid. It finishes at the same height but not the same point because I'm using the same amount of magnesium. Let's just remove those circles because I don't really need them going forward. Right, next, the red line. The red line. Now, first off, always, if you can, compare to the first line that you've been given, i.e. the line you have been given, the line that the examiner gave you. So I'm going to be comparing this red line with this black line. What has changed? Well, what hasn't changed? Excess 1 mole per dm cubed HCl. So I'm using the same amount of HCl at the same concentration. So I haven't messed around with the concentration at all. What have I messed around with? Well, I'm using 1 gram of magnesium instead of 2 grams. I'm using magnesium ribbon instead of magnesium powder. Now, those are two separate things, and there's going to be a little alarm going off in your brain going, but I can't change two things, that's not going to make it a fair test. Well, in this case, you can actually change two things because those two things are changing significantly different parts of the experiment, so can be dealt with separately. Let's deal with the ribbon bit first. The magnesium ribbon. Why is it important that we're using ribbon? Well, what are we changing with ribbon? Ribbon, we are changing the surface area. And if we've gone from powder to ribbon, the surface area has decreased significantly. If you think about it, powder, there's lots of little bits, you can touch all of the lots of little bits. If it's a ribbon, you can only touch what's on the outside of the ribbon, you can't touch all of the atoms that are on the inside of the ribbon. So we are decreasing the surface area, which means we are going to decrease the rate against the first line, which means the initial rate is going to be lower. So our initial gradient is, just like with the blue line, going to be shallower than the black line. We can't compare it to the blue line, and the examiner would not compare it to the blue line. So you might have your red line slightly steeper than the blue line or slightly shallower than the blue line. It doesn't actually matter as long as it is shallower than the black line. So that's one bit. We need to start off shallower. Right. We are using 1 gram of magnesium and excess acid. We used excess acid all the time, so we're using half the amount of reagent that gets all used up, the stuff that's not in excess. If we use half the amount of reagent, we're going to produce half the amount of product. Now, this hasn't been particularly helpfully drawn in on the graph for us, but if we look up here, we go 1, 2, 3, 4 whole blocks, and then we are 2 little blocks shy of the top. So that's going to be 8 blocks, 8 little blocks up here. So we've got 4 whole blocks and 8 little blocks, which means that halfway up is going to be 2 of the big blocks and 1, 2, 3, 4 of the little blocks. So we are going to start off shallower because we are decreasing our surface area, and we're going to finish with half the amount of product because we started with half the amount of reagents. So there we go. And if in doubt, you can mark this up as X and 2x to show that you know that we have produced exactly half the amount. So rate graphs. Quite simply, the rate is given by the gradient. The gradient is always going to be decreasing for a normal type of reaction because we're going to be using up reactant particles, so we're going to have less collisions per unit time, less successful collisions per unit time. The rate will decrease the whole way through. And when looking at changing the variables, we need to look at both the variable that gets changed. Is it going to increase or decrease the rate of the reaction? Is it going to increase or decrease the steepness at the beginning? We get 1 mark for the steepness at the beginning, and we get 1 mark for where we finish the reaction. Where we finish? That's the amount. So this is governed by the variable, and this is governed by the amount of reagent. And if you can do that, you can practice that, you're going to do very well in these questions.